Welcome to week 7, lecture 3 of Math 320. As of the last lecture, we finished our discussion of sequences in this course. In the 2 remaining lectures of this week, we will discuss some stuff about series. The concepts should be less foreign to you since the statements that we will touch on closely resemble those that you have previously seen in a calculus course. The emphasis of our discussion are not the theorem statements themselves, but how these theorems can be proved using what we already learned about sequences and their convergence. If you follow this course by looking also at the textbook, you will see that we are jumping ahead a little bit now to pages 95 through 98 in this lecture. Okay, let's get started. First, a very quick review of the sigma or summation notation. Throughout, we will use xn to denote a sequence. The sigma notation has several components. There is the capital sigma sign, which indicates that we are trying to do a sum. Below the sigma, we see it written n equals m. This means that we're using n as the index with respect to do the summation, and we will start with the first index being m. The reason that we include the n equals in the notation is the same reason as why when we write a sequence as how you see in the middle of the slide, we use an n subscript outside the parentheses to indicate the index. The reason is that our expression may include more than one variable in it, and so it increases clarity to reduce confusion if we specify precisely which variable or symbol we are using for the index of the terms to be summed. Above the sigma sign, we see the letter m. This is the final index that should be summed. And to the right, we have x sub n. This represents the sequence to be summed. Frequently, this will be replaced by an explicit formula for the sequence. The sigma notation means to sum the sequence starting from the index small m, ending at the index big M. If we expand everything, this should look like the sum of the finitely many terms x sub m plus 1, plus x sub m plus 2, and so on, all the way to x sub capital M. Customarily, we always write the lower bound below the sigma sign and the upper bound above it. The idea of the infinite series is trying to make sense of what happens if we allow the summation to go off to infinity. Customarily, we write infinity for the upper bound index in the sigma notation when this happens. Now, we cannot just add infinitely many numbers together, so we should understand this symbol as a shorthand for a process that allows us to perform this addition. Infinite series are precisely these kinds of summations. To understand infinite series, we need to understand how to make sense of a sum of infinitely many numbers. What we do know how to make sense of is the sum of finitely many numbers. So naturally, we ask whether we can start by taking sums of finitely many numbers and then increasing the numbers and then try to take the limit. And we have already developed an idea of what taking the limit looks like for sequences. So what we need to do is just to transform the series process into something we can handle using the sequence process. To do so, we first define what are called the partial sums of an infinite series. Frequently, we denote this using S sub m. S sub m is the sum of the first m terms of the infinite series corresponding to our sequence x sub n. Namely, it is the sum of x sub 1 plus x sub 2 plus x3 plus all the way up to xm. It is a sum of a part of the series, hence the name partial sum. By doing this for every natural number m, we see that S sub m forms itself a sequence. So, we will say that an infinite series converges if the corresponding sequence of partial sums converge as a sequence. And when the convergence happens, we will set the value of the infinite series to equal the value of the limit of the sequence of partial sums. And when the sequence of partial sums diverges, then we also say that the infinite series diverges and the sum has an undefined value. Make sure to draw mentally the distinction between the sequence that we are summing, which we're using x sub n to notate, and the sequence of partial sums, which we write as s sub m, and which we use to help us define what convergence means for infinite series. A simple example is that of the geometric series. Let us look at the series whose nth term looks like r raised to the power n. First, we can write down its corresponding partial sums. S sub m is r plus r squared plus r cubed plus and so on until r to the power m. In order to understand how the series behaves, we need to understand how the sequence behaves. Since we have an infinite sum since we have a finite sum for S sub m, we can do ordinary algebra on the finite sum with no problems. And here we do some basic computations. In order to understand the term S sub m, we first multiply it by the quantity 1 minus r. When we do the algebra and FOIL the product, we see that it looks like r plus r squared plus r cubed and so on until r to the power m, subtract r squared minus r cubed minus and so on until r to the power m plus 1. Notice that the middle terms all come in pairs and cancel each other. So only the head and the tail are left, which we simplify to r minus r to the power m plus 1. Whenever r is not equal to 1, we can divide by 1 minus r to conclude that S sub m is equal to the quantity r over 1 minus r minus r to the m plus 1 over 1 minus r. Notice that when r is in fact equal to 1, then 1 to the power n is always 1, so the partial sum is just a sum of m copies of 1, so that S sub m equals m. Having established formulae for the partial sums, we can try to take its limits. This will show us whether the corresponding series converges or not. We separate into cases. When r equals 1, then we know S sub m equals m. This sequence diverges since it grows unboundedly. This means the geometric series with r equals 1 diverges. When r is larger than 1 in absolute value, we write S sub m equals r over 1 minus r minus r over 1 minus r times r to the power m. The first term is a constant independent of m, so it's harmless when we take the limit in m. The main part that is involved is the expression r to the power m. When r in absolute value is greater than 1, r to the power m grows unboundedly. And so the sequence of partial sums diverge, and so the series diverges. When r is minus 1, the partial sum looks like, after some simplification of algebra, minus 1 half plus 1 half times minus 1 to the power m. This sequence of partial sums has terms minus 1, 0, minus 1, 0, minus 1, 0, and so on. And we see that it has lim sup 0 and lim inf minus 1, and so does not converge. And finally, when r is less than 1 in absolute value, using that r to the power m converges to 0 as m goes to infinity, we see that the sequence of partial sums converge to r over 1 minus r. And hence, in this case, we say that the infinite geometric series converges to r over 1 minus r when r in absolute value is less than 1. You probably have seen something like this already in your calculus class. Now, the series for which the sequence of partial sums have explicit formulae that are easy to evaluate are few and far in between. Most of the time, the sequence of partial sums cannot be easily computed in a neat formula. And so we have to rely on more abstract methods to study the sequence of partial sums. And as we have learned in our study of sequences, a very powerful method is the method of Cauchy's criterion. Cauchy's criterion states that a sequence converges if and only if it is a Cauchy sequence. And just to remind ourselves, a sequence is Cauchy if for every epsilon positive, there exists some index n such that for any two chosen indices beyond the index n, the difference of the corresponding terms is no more than epsilon. Applying Cauchy's criterion to the sequence of partial sums, we see that the infinite series converges if and only if its sequence of partial sums form a Cauchy sequence. Now, the determiner of a Cauchy sequence is this paired difference between terms, s sub j minus s sub k. We can expand this difference, assuming j is bigger than k, otherwise we switch the order, using the definition of partial sums. S sub j is the sum of the first j elements of the sequence x, S sub k is the sum of the first k elements, so S sub j take away S sub k is the sum of the elements of the sequence x starting from the term k plus first to the jth. So, to summarize everything so far, we have the theorem. The infinite series summing x sub n converges if and only if for every epsilon positive, there exists an index n such that for every j larger than k larger than n, the sum from the kth to the jth term of xn and taking in absolute values is less than epsilon. Note that the absolute value is applied after taking the sum, not before. In the next lecture, we will start from this consequence of the Cauchy criterion and derive some of the more common series convergence tests. This theorem is, in fact, the foundation for most studies of convergence in infinite series. Notice also that in the case when j and k are equal, then the sum collapses to just a single term x sub k. So, in particular, this theorem states that if an infinite series converge, then for every epsilon, there exists an index n such that for every index k larger than n, the single term x sub k is less than epsilon in absolute value. This is in fact the nth term test for divergence you learned about in calculus classes. That if an infinite series converges, then the sequence that makes up the terms to be summed converges to zero as a sequence. Very importantly, do not confuse the sequence convergence here, which applies to the sequence of terms that are being summed, with the sequence convergence of the partial sums. One final concluding note, the theorem before, just as Cauchy's criterion, is a by implication. It states that the series converges if and only if something happens. The corollary, however, only goes in one direction. It says that if the series converges, then something happens, but not the reverse. This is because when deriving the corollary, we did not use the full power of the theorem. The conclusion that the sequence x sub n converges to zero only uses a small part of the Cauchy criterion. It only used the part when j is equal to k. The Cauchy criterion allows j and k to be arbitrary as long as they are both bigger than the threshold capital N. It is because only partial information is used that the corollary goes only one way and is weaker than the full criterion. What is worth emphasizing again is that the reverse implication is not true. Just because a sequence x sub n converges to 0 doesn't mean that the infinite series converges. There are plenty of sequences for which the terms converge to 0, but the infinite series diverges. One can, however, make use of the contrapositive of the corollary to say that if a sequence x sub n is such that it diverges, or that it converges to a non-zero value, then the infinite series must diverge. Okay, we'll end here for this lecture. See you next time.